Hello and welcome to week 6 in database systems. Jumping right into our agenda. First, we'll go over the assignments for this week, and then we'll talk about chapters 14 and then chapters 15. First, the assignments. Week 6 centers on chapter 14, which deals with basic functional dependencies and normalization for relational databases. Chapter 15 deals with relational database design, algorithms, and further dependencies. Your first discussion for this week is about chapter 14, where you talk about object and object relational databases. In the second discussion, chapter 15 is about relational database design algorithms. Also, remember the practical connection assignment is due week 6 as well at the end of this week. Week 6 objectives include informal design guidelines for relational databases, functional dependencies, the definition of functional dependencies, and normal forms based on primary keys, general normal form definitions such as second normal form and third normal form, Boyce-Codd normal form, multi-value dependencies in fourth normal form, and then join dependencies in fifth normal form. Chapter 15 talks about further topics in functional dependencies, properties of relational decomposition, algorithms for relational database schema designs, nulls, dangling tuples, alternative rational designs, multi-value dependencies, and fourth normal form, further discussion. Moving on to week 6, discussion number 1, discuss insertion, deletion, and modification anomalies. Why are they considered bad? Illustrate with examples. The second discussion for week 6 is around chapter 15, which is what is meant by closure of a set of functional dependencies. Illustrate with an example. The practical connection assignment is intended to show how this course deals with things in your real world setting. So with that in mind, provide a reflection of at least 750 words, which is roughly 2.5 pages double spaced, of how the knowledge, skills, and theories of this course would have been or could have been applied or can be applied or will be applied in a practical manner to your current work or future work if you're not currently working. If you are not currently working, share times when you have or could observe these theories and knowledge could be applied to an employment opportunity in your field. Again, 750 words, 2.5 pages, and a minimum reflection. Do use APA formatting and citations, although in this situation, a citation is really probably not going to be necessary. This is something that should be about your personal reflection on what this course is about and how it relates to what you do on a day-to-day basis. You don't have to explain to me what all the concepts are, but you do need to demonstrate how they do reflect in your real-world setting. Make sure that you do your own work and do not copy someone else's submission. I have seen that in the past. It really makes no sense to me because this is a relatively straightforward assignment. Just tell me what this class has to do with your job. So it should be fairly straightforward. If it doesn't for some reason have something to do with your job, think about how it could in the future. Chapter 14 is about the basics of functional dependencies and normalization of relational databases. The learning objectives are sections 14.1, which deals with informal design guidelines for relational databases, section 14.2, which deals with functional dependencies, and 14.3, which deals with normal form based on primary keys, 14.4, which deals with general normal form definitions for second and third normal form, and Boyce-Codd normal form. 14.6 is about multi-value dependencies with fourth normal form, and 14.7 is around join dependencies with fifth normal form. 14.1 is about informal design guidelines for relational databases. So what is a relational database design? And it's basically the grouping to form a good relational schema. There are two levels of relational schemas, the logical, which is user view, and the storage, which is a base relation level. The design is concerned mainly with base relations. What are the criteria for good base relations? Well, we first discuss informal guidelines for good relational data design, then we'll discuss formal concepts of functional dependencies and normal forms, and then additional types of dependencies, further normal forms, relational design, algorithms by synthesis are discussed in chapter 15. The semantics of the relational attributes must be clear. Guideline 1, informally, each tuple in a relation should represent one entity or relationship instance. This applies to individual relations and their attributes. Attributes of different entities, employees, departments, and projects, and so on, should not be mixed in the same relation. Only foreign keys should be used to refer to other entities. Entities and relationship attributes should be kept apart as much as possible. The bottom line is that you should design a schema that can be explained easily relation by relation. The semantics of attributes should be easy to interpret. Here's an example of 14.1, figure 14.1 of a simplified company relation database schema. 14.1.2, redundant information tuples and update anomalies. Information is stored redundantly. It's wasteful of storage. It causes problems with update anomalies, insert anomalies, deletion anomalies, and modification anomalies. Consider the relation employee project, employee number, project number, employee name, project name, and number of hours. An update anomaly is changing the name of the project number P1 from billing to customer accounting may cause this update to be made for all 100 employees working on project 1. Consider the relation employee project as well. An insert anomaly cannot insert a project unless one employee is assigned to it. Conversely, cannot insert an employee unless he or she is assigned to a project. A deletion anomaly is when a project is deleted, it will result in deleting all the employees who are working on that project. Alternatively, if an employee is the sole employee in a project, deleting that employee would result in deleting the corresponding project. Figure 14.3 is a two-relation schema suffering from an update anomaly. Figure 14.4 is sample states for employee department and employee project. Guidelines for redundant information in tuples and update anomalies. Guideline number 2 is design a schema that does not suffer from the insertion, deletion, and update anomalies. If there are any anomalies present, then note them so that applications can be made to take them into account. Guideline number 3 deals with null values and tuples. Relations should be designed such that their tuples will have as few null values as possible. Attributes that are null frequently can be placed in separate relations with the primary key. Reasons for null include attributes not applicable or invalid, attribute values unknown, or the value known to exist but is unavailable. 14.1.4 is the generation of spurious tuples, and avoid this at any cost. Bad designs for a relational database may result in erroneous results from certain join operations. The lossless join property is used to guarantee meaningful results for join operations. Guideline number 4 is the relations should be designed to satisfy the lossless join condition. No spurious tuple should be generated by doing a natural join of any relations. There are two important properties of decompositions. One is the non-additive or lossless of the corresponding join. The second is preservation of the functional dependencies. Note that a property A is extremely important and cannot be sacrificed. Note that property B is less stringent and may be sacrificed. This is discussed in chapter 15. Functional dependencies are used to specify formal measures of the goodness of relational design and keys are used to determine normal forms for relations, are constraints that are derived from meaningful meaning and interrelationships of data attributes. A set of attributes X functionally determines a set of attributes Y if the value of X determines a unique value for Y. X implies Y holds if whenever two tuples have the same value of X, they must have the same value of Y. For any two tuples T1 and T2 in any relational instanceship R sub big R, if T sub X or of X and equals T2 of X, then T1s of Y must equal T2 of Y. X implies Y is in R specifies a constraint on all relational instances of R. Written as X implies Y can be displayed graphically on a relation schema as in figures denoted by the arrow. Functional dependencies are derived from the real-world constraints on the attributes. An example of constraints, Social Security numbers determines employee name, project number determines project number, employee Social Security and project number determines the hours per week that the employee works on the project. A functional dependency is a property of the attributes in the schema R. The constraint must hold every relation instance of R. If K is a key of R, then K functionally determines all attributes in R, since we never have two distinct tuples with T1 sub K equals T2 sub K. Defining functional dependencies from instances, note that in order to define functional dependencies, we need to understand the meaning of the attributes involved and the relationship between them. And a functional dependency is a property of the attributes in the schema R. Given the instance population of a relation, all we can conclude is that a functional dependency may exist between certain attributes. What we can definitely conclude is that certain functional dependencies do not exist because there are tuples that show a violation of these dependencies. Figure 14.7 is about ruling out functional dependencies. Note that given the state of the teach relation, we can say that the functional dependency text implies course may exist. However, the functional dependency teacher implies course, teacher implies text, and course implies text are ruled out. A relation R of A, B, C, D with its extensions, which functional dependencies exist on this relation or in this relation. Normal forms based on primary keys. 3.1 talks about normalization of relations. 3.2, practical use of normal forms. 3.3, definition of keys and attributes participating in keys. 3.4, first normal form, second and third. So normalization is the process of decomposing unsatisfactory bad relations by breaking up their attributes into smaller relations. Normal form condition using keys and functional dependencies of a relation to certify whether a relation schema is in a particular normal form. Second, third, and fourth normal form are based upon keys and functional dependencies in a relational schema. Fourth normal form is based upon keys and multi-value dependencies, and fifth normal form is based on keys and join dependencies. Additional properties may be needed to ensure a good relational design, lossless join, dependency preservation, and so on. See Chapter 15. Normalization is carried out in practice so that the resulting designs are of high quality and meet the desirable properties. The practical utility of these normal forms becomes questionable when the constraints on which they are based are hard to understand or to detect. The database designers need not normalize to the highest possible normal form. Usually third normal form or Boyce-Codd normal form, rarely to use fourth normal form, and almost never use fifth normal form. Denormalization is the process of storing the data, the join of higher normal forms in a base relation, which is a lower normal form. Sometimes you will denormalize for performance reasons. A superkey is a relational schema of a relational schema is R of A through N, a set of attributes S, subset of R, with the properties that no two tuples T1 and T2, any legal relation state R, will have T sub 1 S is equal to T sub 2 of S. A key is a superkey with the additional property that removal of any attribute from K will cause K not to be a superkey any longer. If a relation schema has more than one key, each is called a candidate key. One of the candidate keys is arbitrarily designated to be the primary key, and the others are called secondary keys. A primary attribute must be a member of some candidate key. A non-prime attribute is not a prime attribute. That is, it is not a member of any candidate key. Disallows composition attributes, multi-valued attributes, and nested relations. This is first normal form. Attributes whose values of an individual tuple are non-atomic. It's considered to be part of the definition of a relation. Most RDBMSs allow only those relations to be defined that are in first normal form. Figure 14.9 is the normalization into first normal form, or relational schema that is not in first normal form. B, sample state of relation department. C, first normal form version of the same relation with redundancy. Figure 14.10, normalization nested relationships into first normal form. A, schema of the employee project relation with a nested relation attribute projects. B, sample extension of the employee project relation showing nested relations within each tuple. Decomposition of employee project into relations, employee project 1 and employee project 2, propagating the primary key. Second normal form uses the concept of functional dependencies and primary keys. The definition, a primary attribute, an attribute that is the member of the primary key K. Full functional dependency, a functional dependency Y implies Z, where not removal of any attribute from Y means that the functional dependency does not hold any longer. An example is social security number and phone number implies hours. Is a full functional dependency since neither social security number hours nor phone number hours hold. The social security number, phone number, or project number, sorry, not project, project number implies name is not a full functional dependency. It is called a partial dependency since social security number implies name also holds. So project number is not needed to determine name. However, the combination of social security number and project number is implied for hours. A relational schema R is in second normal form if every non-prime attribute A is R in R is fully functionally dependent upon the primary key. R can be decomposed into second normal form relations via the process of second normal form normalization or second normalization. Figure 14.1 is normalizing second normal form and third normal form. 14.12, normalization of second normal form and third normal form. Third normal form. The definition is a transitive functional dependency. A functional dependency X implies Z can be derived into two functional dependencies, X implies Y and Y implies Z. Example is social security number it implies DMG R SSN is a transitive functional dependency since social security number implies D number and D number implies D manager SSN holds. SSN implies name is non-transitive since there is not a set of attributes X where SSN implies X and X implies name. A relational schema R is in third normal form if it is in second normal form and no non-primary attributes A in R is transitively dependent upon the primary key. R can be decomposed into third normal form via the process of third normal form normalization. Note, in X implies Y and Y implies Z, X is the primary key, and consider this is a problem only if Y is not a candidate key. When Y is a candidate key, there's no problem with the transitive dependency. For example, consider EMP, employee, social security number, employee number, salary. Here, social security number implies employee number, implies salary, and employee number is a candidate key. Normal forms defined informally. First normal form, all attributes depend on the key. Second normal form, all attributes depend on the whole key. Third normal form, all attributes depend on nothing but the key. 14.1 General normal form definitions for multi-keys. The above definitions consider the primary keys only. The following more general definition take into account relations with multiple candidate keys. An attribute involved is a candidate key, and a candidate key is a primary attribute. All other attributes are called non-primary attributes. 14.4.1 general definition of second normal form for multiple candidate keys. A relation schema R is in second normal form if every non-primary attribute A in R is fully functional dependent upon every key in R. For example, figure 14.1.2, county name implies tax rate involves second normal form. So second normalization converts lots into lots 1, property number, and so on. 14.4.2 General definitions of third normal form. Definition: a superkey of a relation schema R, a set of attributes S of R that contains a key of R. A relational schema R is in third normal form if, whenever a functional dependency X holds for A, functional dependency X implies A holds in R for either X is a superkey of R or A is a prime attribute of R. Lots 1 relational violates third normal form because area implies price and area is not a superkey in lots. Consider the two conditions of the definitions of third normal form. A relation schema R is in third normal form if, whenever a functional dependency A, X implies A, holds in R, then either X is a superkey of R or A is a prime attribute of R. Condition A catches two types of violations. One where a primary attribute functionally determines a non-primary attribute. This catches second normal form violations to non-full functional dependencies. Second, when a non-primary attribute functionally determines a non-prime attribute. This catches third normal form violations due to a transitive dependency. As an alternative definition of third normal form, we can restate the definition as a relational schema R is in third normal form if every non-prime attribute in R meets both of these conditions. It is a fully functionally dependent on every key of R. It is a non-transitive dependent on every key of R. Note that stated this way, a relation in third normal form meets the requirements of second normal form. The condition B from the last slide takes care of the dependencies that slip through, are allowable to third normal form, but are caught by Boyce-Codd normal form in the next discussion. Boyce-Codd normal form is a relational schema R is in Boyce-Codd normal form, BCNF. If, whenever a functional dependency X implies A holds in R, then X is a superkey of R. Every normal form is strictly stronger than the previous one. Second normal form relation is in first normal form, third normal relation is in second normal form, and Boyce-Codd normal form is in third normal form. There exist relations that are in third normal form, but not in Boyce-Codd normal form. Hence, BCNF is considered a stronger form of third normal form. The goal is to have each relation in BCNF or third normal form. Figure 14.3 is a Boyce-Codd normal form description. This is a 14.14 is a relation that teach that is in third normal form, but not in BCNF. Achieving the BCNF by decomposition. Two functional dependencies exist in relation teach. FD1 is student, course implies instructor. Functional dependency 2 is instructor implies course. Student course is a candidate key for this relation, and that the dependencies shown follow the pattern in figure 14.13. So this relation is in third normal form, but not in BCNF. A relation not in BCNF should be decomposed so as to meet this property while possibly foregoing the preservation of all functional dependencies in the decomposed relations. Three possible decompositions for relation teach is decomposition 1 is student instructor and student course. The second is course instructor and course student. The third is instructor course and instructor student. All three decompositions will lose functional dependence 1. We will have to settle for sacrificing the functional dependency preservation, but we cannot sacrifice the non-additivity property after decomposition. Out of the above three, only the third decomposition will not generate subplurus tuples after join, and hence has the non-additive property. A test to determine whether a binary decomposition to two relations is non-additive, lossless, is discussed under property NJB on the next slide. We then show how the third decomposition above meets the property. Testing binary decomposition for lossless join, non-additive join, property, binary decomposition, decomposition of a relation R into two relations, property NJB, non-additive join test for binary decompositions, a decomposition, and so on. Test for checking non-additive of binary relation decompositions. If you apply the NJB test for the three decompositions of the teach relation, D1 gives student implies instructor, student implies course, none of which is true. D2 gives course implies instructor, course implies student, none of which is true. However, D3, we get instructor implies course and instructor implies student. Since instructor implies course is indeed untrue, NJB property is satisfied and D3 is determined to be as a non-additive, a good decomposition. Here we can make the use of the algorithm from chapter 15, algorithm 15.5. Let R be the relation not in BCNF, let X be a subset of R, and let X imply A be the functional dependency that causes a violation of BCNF. Then R may be decomposed into two relations, R A and R and X intersection A. If neither R minus A or X intersection or union A is not BCNF, repeat the process. Note that the functional dependency that violates BCNF in teach was instructor implies course, hence its BCNF decomposition would be teach minus course and instructor union course, which gives the relations instructor student and instructor course that we obtained before decomposition D3. Multi-valued decomposition, the dependencies in fourth normal form, multi-valued dependencies, MVD, just skip over that. A relation schema R is in fourth normal form with respect to a set of dependencies F that includes functional dependencies and multi-valued dependencies. If for every non-trivial multi-valued dependency, Y is in X plus, X is a superkey for R. Note F plus is the complete set of all dependencies, functional or multi-valued, that will hold in every relation state R that satisfies F. It also is called a closure of F. Figure 14.4 is about fourth and fifth normal forms. 14.7, joint dependencies in fifth normal form. This is the definition of a joint dependency. A relational schema R is in fifth normal form or project join normal form with respect to a set of F functional multi-valued and join dependencies if for every non-trivial join dependency that is implied by F, every R sub I is a superkey of R. Chapter summary. We've talked about what informal design guidelines for relational databases. We talked a bit about functional dependencies. We talked about various forms of normalization, general normalization form definitions, second and third normal form, multi-key values, BCNF and fourth normal form, and fourth and fifth normal forms. One of the things you will see most of the time is that things are going to be in third normal form, maybe Boyce-Codd normal form, but typically third normal form. There are times that you actually denormalize either through persisted views or potentially just a view for performance reasons, because a lot of times joins can be expensive and sometimes you will flatten things out so that things are faster, even if you're potentially losing a certain amount of optimization around the dependencies. Chapter 15 deals with relational database design and algorithms and further dependencies. Here are the sections we'll be going over. 15.1 through 4, and then 15.5 and 6. Functional dependencies, inference rules, and equivalence and minimum cover. We discussed functional dependencies in the last chapters. To recollect, a set of attributes of X, X functionally determines a set of attributes Y if the value of X determines a unique value of Y. Our goal here is to determine the properties of functional dependencies and to find out the ways of manipulating them. X implies Y holds if every two tuples have the same value for X, they must have the same value for Y. For any two tuples T1 and T2, if any relational instance R sub R, if T1 sub X is equal to T2 of X, then T1 of Y is equal to T2 of Y. X implies Y with an R specifies a constraint on all relational instances written as X implies Y can be denoted graphically as a relational schema as in figures in chapter 14 denoted by an arrow. Functional dependencies are derived from the real world constraints of the attribute. Definition inference rules for functional dependencies. X implies Y is inferred from or implied by a set of dependencies F specified in R if X implies Y holds in every legal relation state R of R. That is, every R satisfies all the dependencies in F, X implies Y also holds in R. Given a set of F functional dependencies F, we can infer additional functional dependencies that hold whenever FDs in F hold. Armstrong's inference rules are as follows. Inference rules for functional dependency, some additional inference rules that are useful. Decomposition, X implies YZ, then X implies Y, and X implies Z. Union, if X implies Y, then X implies Z, then X implies YZ. And pseudotransitivity, if X implies Y and WY implies Z, then XY or WX implies Z. The last three inference rules, as well as any other inference rules, can be deduced from IR 1, 2, and 3 through the completeness property. A closure of a set of functional dependencies F is the set of F plus for all FDs that can be inferred from F. A closure of a set of attributes X with respect to F is the set X plus for all attributes that are functionally determined by X. X plus can be calculated by repeatedly applying IR 1 through 3 using functional dependencies in F. Algorithm 15.1 is around determining X, the closure of X under F. The input is the set of F's in the functional dependency in the relational schema R, and a set of X, which is a subset of R, X plus X, and then repeat, and then so on. Example closure. For example, consider the following relational schema about classes held at university in a given academic year. The closure of attributes or sets of attributes of some example sets. Two sets FDs, F and G, are equivalent if for every F can be inferred from G and FG and G can be inferred from F. Hence, F and G are equivalent to F plus equals G plus. Definition covers F covers G, and every functional dependency in G can be inferred if F and G are equivalent. F and covers G, and so on. Finding minimal cover of functional dependencies. Just as we applied inference rules to expand on a set of FDs to arrive at F closure, it is possible to think in the opposite direction to see if we can shrink or reduce the set F to its minimal form so that the minimal set is still equivalent to the original set F. Definition: an attribute is a functional dependency is considered extraneous attribute if we can remove it without changing the closure of the set of dependencies formerly given. F, the set of functional dependencies, and a functional dependency X implies A. If F attribute Y is extraneous, if X in X, if Y is a subset of F of X and X logically implies. A set of FDs is minimal if it satisfies the following conditions. Every dependency in F has a single attribute for its RHS. We cannot remove any dependencies from F and have a set of dependencies that is equivalent to F. We cannot replace any dependencies X implies A in F with a dependency Y implies A's, where Y is a proper subset of X, and still have a set of dependencies that is equivalent to F. Algorithm 15.2, finding the minimal cover F of a set of functional dependencies E. Illustration of the algorithm 15.2 is as follows. We now have a set equivalent to the original E, say E prime. B implies A, D implies A, B implies D. No further reduction is possible in step 2 since all functional dependencies have a single attribute on the left-hand side. Minimal set of FDSs. Every set of FDSs has a equivalent minimal set. There can be several equivalent minimal sets. There is no simple algorithm for computing a minimal set of FDs that is equivalent to a set F of FDs. The process of algorithm 1512 is used until no further reduction is possible. To synthesize a set of relations, we assume that we start with a set of dependencies that is a minimal set. Designing a set of relations. The approach of relational synthesis bottom-up design assume that all possible functional dependencies are known, construct a minimal set of functional dependencies, then apply algorithms that construct a target set of third normal form or Boyce-Codd normal form relations. Additional criteria may be needed to ensure that the set of relations in a relational database are satisfactory. See algorithm 15.3. The goals is a lossless join property. It's a must. Algorithm 15.3 test for general losslessness. Dependency preservation property, observe as much as possible. Algorithm 15.5 decomposes the relation into Boyce-Codd normal form components by sacrificing the dependency preservation. Additional normal forms, fourth normal form based on multi-valued dependencies, and fifth normal form based on joint dependencies. Algorithm to determine the key of a relation. Algorithm 15.2a, finding a key K for R given a set of F's of functional dependencies is as follows. 15.2, properties of relational decomposition. 2.1, relational decomposition and insufficiency of normal forms. The universal relational schema, a relational schema R of A1 through N that includes all the attributes in the database. Universal relation assumption, every attribute name is unique. Decomposition, the process of decomposing the universal relational schema R into a set of relational schemas, D equals R sub 1 through N, that will become the relational database schema by using the functional dependencies. Attribute preservation condition, each attribute in R will appear in at least one relation schema R in the decomposition so that no attributes are lost. Properties of relational decomposition, third of 11. Another goal of decomposition is to have each individual relation R in the decomposition D be in B, C, and F or third normal form. Additional properties of decomposition are needed to prevent from generating spurious tuples. 2.1, dependency preservation property of a decomposition. Definition, given a set of dependencies F on R, the projection of F on R1 or Ri denotes by P sub RIF, where Ri is a subset of R, is the set of dependencies X in that implies Y in F closure such that the attributes in X union Y are contained in Ri. Hence, the projection of F in each relation schema R in the decomposition D is the set of functional F closure dependent upon the closure of F such that all their left and right-hand side attributes are in R sub I. Dependency preservation of a decomposition continued. Dependency preservation property, a decomposition D equals R sub 1 through M of R is dependency preserving with respect to F if the union of the projections of F on each R sub I in D is equivalent to F, that is, and so on. The claim 1, it is always possible to find a dependency preserving decomposition D with respect to F such that each relation Ri in D is in third normal form. This is a Boyce-Codd normal form dependency diagram. Figure 14.12 is the normalization of second normal form and third normal form in the second screen. Properties of relational decomposition, non-additive lossless join property of a decomposition. Definition, lossless join property, a decomposition D of R1 through M of R has lossless non-additive join property with respect to the set of dependencies F on R if for every relation state R of R that satisfies F, the following holds where star is the natural join of all of the relations in D. Note that the word loss and lossless refers to the loss of information, not the loss of tuples. In fact, the loss of information is better termed in addition of spurious information. Algorithm 15.3, test for the lossless join property. Repeat the following. This is a continuing on of that process. Figure 15.1 is the non-additive join test of n-ary decompositions. Testing binary decompositions of non-additive join, lossless join property, binary decomposition of relation into two relations. Property in NJB is the non-additive join test for binary decompositions, and so on. Successive non-additive join decomposition. Claim 2, preservation of non-additive in successful decompositions. If a decomposition D sub R1 through N M of R has the lossless non-additive join property with respect to a set of functional dependencies F on R, and if a decomposition Di of Q1 through K of Ri has the lossless non-additive join property with respect to the projection of F on R sub I, then the decomposition D2 is equal to R1 through M of R that has the non-additive join property with respect to F. Algorithm 15.4 is the relational synthesis of third normal form with dependency preservation and non-additive lossless join property. Algorithm 15.5, relational decomposition into BCNF with lossless non-additive join property. 15.4, problems with null values and dangling tuples. Problems with null values. When some tuples have null values for attributes, they will be used to join individual relations in the decompositions that may lead to incomplete results. For example, figure 15.2a, where two relations employee and department are shown, the last two employee tuples represent newly hired employees who have not yet been assigned to a department. Assume that this does not violate any integrity constraints. If we want to retrieve a list of employee name, department number, values for all employees, if we apply a natural join operation on employee and department, the two aforementioned tuples will not appear in the results. As in such cases, a left outer join may be needed. The results are shown in 15.2c. Continuing the discussion of problems with dangling tuples, consider the decomposition of employee into employee 1 and employee 2 as shown as figure 15.3a and b. Their natural join yields the original relation employee in figure 15.2a. We may use the alternative representation shown in 15.3c, where we do not include a tuple in employee 3 if the employee has not yet been assigned to a department, instead of including a tuple with a null for denom as in employee 2. If we use employee 3 instead of employee 2 and apply a natural join on employee 1 and 3, the tuples in Berger and such will not appear in the results. This is called dangling tuples in employee. Discussions of normalization algorithms. Problems. The database designer must first specify all the relevant functional dependencies among the database attributes. These attributes are not deterministic in general. It is not always possible to find a decomposition into relational schemas that preserves dependencies and allows each relational schema in the decomposition to be in BCNF instead of third normal form as in algorithm 15.5. A multi-value dependency, MVD, X implies Y, specifies on a relationship R where X and Y are both subsets of R, specifies the following constraint of any relation state R of R. If two tuples T1 and T2 exist in R such that T1 sub X minus T2 sub X, then two tuples T3 and T4 should also exist in R. The following properties where we use Z to denote and so on. Inference rules for functional multi-value dependencies are as follows. A relational schema R is in fourth normal form with respect to a set of dependencies F that includes functional dependencies and multi-value dependencies if for every non-trivial multi-value dependency, X implies Y, in F closure, X is a superkey of R. A definition of fifth normal form, a relational schema R is in fifth normal form or project join normal form, PJ and F, with respect to a set of F functional, multi-valued, and join dependencies if for every non-trivial join dependency, that is F implied by F, every R sub I is a superkey of R. Discovering join dependencies in practical databases with hundreds of relations is next to impossible. Therefore, fifth normal form is rarely used in practice, if ever. Um, inclusion dependency R.X is less than S.Y between two sets of attributes X of R relations schema R and Y of relation schema S, specifies the constraint that at any specific time when R is in a relational state R and S is in a relational state of S, we must have, and so on. Objective of inclusion dependencies: to formalize two types of interrelational constraints which cannot be expressed using functional dependencies or multi-value dependencies. Referential integrity constraints, class, subclass relations, inclusion dependency inference rules, and so on. Algorithmic functions: as long as the unique value of Y is associated with every value of X, we can still consider that to be a functional dependency, that the functional dependency X implies Y exists. For example, consider the relations order line, order number, item number, quantity, unit price, extended price, and discount price. Each tuple represents an item of an order with a particular quantity and the price per unit for that item. In this relation, quantity unit price implies extended price by the formula. Hence, there is a unique value for extended price for every pair and thus conforms to the definition of functional dependency. Functional dependencies based upon algorithmic functions and procedures. There may be a procedure that takes into account the quantity discount, the type of item, and so on, and computes a discounted price for the total quantity ordered for that item. Therefore, we can say the following. Domain key, normal forms, definition. A relational schema is said to be in DKNF if all constraints and dependencies that should hold on the valid relation states can be enforced simply by enforcing the domain constraints and key constraints for the relation. The idea is to specify, theoretically at least, the ultimate normal form that takes into account all possible types of dependencies and constraints. For a relation in DKNF, it becomes very straightforward to enforce all database constraints by simply checking each attribute value in a tuple to see if the appropriate domain and that every key constraint is enforced. The practical utility of DKNF is limited. To recap, we talked about functional dependencies and revisited them. We talked about designing a set of relations by synthesis. We talked about properties of relational decomposition, algorithms for relational database schema design in third normal form and Boris-Codd normal form. Then we talked about multi-value dependencies in fourth normal form. Other dependencies in normal forms were also discussed. And with that, we've reached the end of this discussion. If you have any questions, feel free to reach out. That's what I'm here for. Otherwise, stay safe, and we'll speak again next week.